So our speaker for the second talk is going to be Lei, who needs audio, so everything is hooked up. Yeah, hopefully. So the talk is called Markit and Talkit, a low-barrier toolkit to augment 3D printed models with audio annotations.
Thank you, Michelle. Today, I would like to introduce Markit and Talkit, a toolkit that can make 3D printed models talk. Markit is a design tool that use to create and modify this talkable model. And Talkit is an application for any user to interact with these models with audio feedback. Before going further into the detail of this toolkit, I would like to take a step back and introduce why we want to make 3D printed models talk and who will benefit from this toolkit. Nowadays, 3D models are becoming more available because of the adoption of 3D printers. These printed models can be very helpful for blind students. Previous studies showed that blind students enjoy learning from this model and achieved exciting learning improvement. However, without additional help, it's actually very hard to understand this model. On a commercial globe model, we can learn geography from its shape, texture, color, and text. However, this is not the case for printed model. As you can see in the slides, the right part is a printed globe model, which has tactile information. But if I'm blind and not so good at geography, how would I know where's Asia and where's America? So blind people will still rely on a sighted person to explain the model to them. So how could we enable blind people to learn these models independently? How about some augmented models that can explain themselves? We are actually not the first group who think about this idea. Some skilled makers already propose some solutions online. For example, they use a conductive filament and electronics to make 3D prints talk. The main idea is that when you touch a conductive part of a model, the electronics will sense your behavior and speak out some audio annotations to you. In this online instruction, we can make a 3D print talk in 12 steps. This would involve printing part of the material in conductive material and assembling, wiring, and sometimes you even need to program the entire annotation manually. As you can see in the video, this activity will involve a lot of devices, effort, and skills. These impractical solutions have two downsides. For makers, although they are willing to help, most of them don't have time or skills to create augmented models. And for blind users, it's also inconvenient to access models with electronics. That's why we created Markit and Talkit. Markit is a design tool that enables makers to quickly add annotations on models. And the Talkit is a computer vision-based program that enables blind people to explore augmented models with audio annotations. Both Markit and Talkit can run on a commodity devices without hardware modification, and they are easy to learn and easy to use. In the remaining time, I'm going to introduce how did we design, evaluate, and build this toolkit. So to design the toolkit, we started with a very simple question. How do blind people want to interact with augmented model? In other words, if models can explain themselves, how would the blind people want to retrieve this audio feedback? To answer the question, we run a design study. It's a comprehensive study to understand user preferred interaction on 3D models. I will talk part of the study today briefly. If you are interested in the detail, you can check out the recently published asset paper, or you can join me next week in Baltimore. So in the study, we invited 12 legally blind participants, and we asked them to suggest different interaction techniques for accessing audio annotations on an augmented model. We found participants commonly mentioned 3 input modalities: gestures, speech, and buttons, and the most common gesture was tapping on an element to retrieve its annotation. For example, on a globe model, they would suggest to tap on a continent to get its name. With the findings from the design study, we designed Toolkit, an application that enables blind people to interact with these augmented models. Users control Toolkit using the common modality from the design study. They use a keyboard to choose which model they want to play, and tap on an element to retrieve its annotation. Meanwhile, they can also use simple speech commands to control and get more information. Now I'm going to show you a video where a user is exploring a globe model using Talkit, and he could use gesture and speech input, and the model will provide audio feedback to get him through the exploration process.
A user can point to an element to get its annotation. He could say more to get a more detailed description.
North America.
More.
North America. North America is to the southeast by South America and the Caribbean Sea.
When he points to two elements, Talkit explains the names and the number of elements. The user can get the relative positions of these elements by saying more.
2. North America, South America.
More.
North America up, South America down.
When he points to an area without an annotation, Talkit says unmarked, indicating the user should move on.
Unmarked, unmarked.
Now I'm going to talk about the technical details about Talkit. How does Talkit enable interactions in commodity devices? Talkit locates a model by finding a special checker, as you can see from the slide. The checker can be printed with 3D printers. To use it, a user needs to slide the checker into the model. And then Talkit uses a Shiri tag library to find the checker from a RGB camera. Since we already have the digital 3D models, the computer can map the 3D model to the 2D video stream based on the checker location. To use gestures, a user needs to put a sticker to his fingernail. Talkit uses a color-based detector to find the fingertip. Then it checks annotation data to provide appropriate audio feedback. To enable speech input, we implemented Talkit's Phoenix library to analyze microphone data. Users can control Talkit using simple commands like more, stop, and start. We implemented the entire system on Python, and the system can run on a MacBook smoothly. So now we got a running system, but how does this system work with our target users, blind people? We are wondering, could blind people find audio annotation using Talkit, and how do they feel about Talkit? To find out the answers for these questions, we recruit 8 legally blind participants. 6 of them identify as blind, while the remaining identify as low vision. In the evaluation study, we first train participants how to use Talkit. Then we ask them to perform 2 tasks. The first task is to get an overview of a model and find all annotated elements on each model. And the second task was to find a target element on each model, and we measure the time. For example, on the globe model, we annotated 5 continents. So in the first task, they need to activate the annotations of all elements. And in the second task, we speak out a name of continent, and they need to activate that specific annotation. And we'll repeat this activity for all 5 continents. In the end, we conduct a short interview to collect feedback. In terms of models, we used a cell model for training, and the participants needed to perform task 1 and task 2 on tank, globe, and the map models. All models have 5 annotated elements. Here are the results. The figures show the time participants spent finding all elements on each model. So this is for the task 1. And the x-axis are 3 models, tank, globe, and the map. And the y-axis is the time. The individual time was plotted as black dots, and the average time for all participants was plotted with a red line. Sorry for the typo here. On average, participants spend 60, 70, and 43 seconds on the tank, globe, and the map models, which means if we give blind participants a model, they could quickly get an overview of this model with the help of Talkit. Complicated and unfamiliar model would require more time to explore. In the study, participants was generally less familiar with tank model. And the longest time across all participants and all models was 176 seconds. Map model is simpler compared to other models because it's basically a 2.5D model. And the shortest amount of time across all participants and models was 16 seconds. In the second test, we find on average it took a participant 7 seconds to find a specific element, which means if a user wants to learn a certain concept or certain element, he could locate that element quickly using Toolkit. During the interview, participants expressed that Toolkit was easy to learn and easy to use and helpful for understanding models. One participant said, "I wish it was around when I was a kid," suggesting how useful Toolkit could be for blind children. However, participants also mentioned they had difficulty understanding models and finding elements. For example, if you don't know what cell looked like before, and I give you a cell model, how would you know what part of the model was annotated and where to find the elements? So in the future, we think we should provide additional audio guidance. For example, when the user gets the model at the very beginning, the system will provide an overview and guide them to go through all the elements in the very beginning. Now we get an application for blind people to interact with augmented models. But how should we create these models? That's where Markit comes into play. Makers use Markit to modify and annotate models. Currently, Markit is implemented as an add-on for Blender, and Blender is an open source software that's free and you can download for any computer. In Blender, as you can see from the slides, each model is represented as triangular faces, and Markit allows a user to annotate a model by selecting and marking these faces. The user interface of Markit has 3 sections. The first section is modification, where a user can add a tracker scaffold, which is used to match the tracker in the Toolkit. And this section also reduces the number of triangular faces to speed up the Toolkit, because sometimes complicated model may have a lot of faces and it cannot be run on commodity devices. This is necessary to enable the Toolkit can run on most devices. In the second section, demarcation, user marks faces in different colors and adds text description. For example, on this tank model, a maker marks the model with 4 colors and with different text description. And the last section is publication, where the user exports the model data. This video shows how to use Markit to annotate a globe model.
Markit enables makers to create augmented models that can be created or downloaded from online communities like Thingiverse or GrabCAD. Once we have a model, a maker can use Markit to easily add annotations. Markit guides the user through a 3-step process. First, the user adds a tracker scaffold to the model and exports a printable file of the modified model. The tracker will be used by the computer vision algorithm in Talkit. Second, the user annotates the model by selecting faces of the 3D model and entering text annotations. And third, the user enters general information about the model and publishes its annotation data.
Okay, so in this video, a researcher annotated a globe model in 5 minutes. But how about people who are not familiar with 3D modeling, like potential makers? To see how potential makers use Markit, we conduct another evaluation study. We want to know how long does it take to add annotations using Markit, and how do makers feel about the Toolkit? We recruit 8 college and graduate students. 4 of them had experience with 3D modeling, but only 1 used the modeling software within last year. After training participants how to use the software, we ask them to annotate 2 elements on each model. For example, on the cell model, we ask them to annotate lysosome and nucleus. In the end, we conduct a short interview. As similar with the previous study, we use a cell model for training, and the participant needed to annotate 2 elements on tank, globe, and map models. The results shows that across all of these models and participants, the mean time to annotate a model was 275 seconds. So how fast is that? Just to give you some reference, it's about the time to boil 1 liter water. So if you are waiting for your hot water or you are making your coffee, do something good and annotate a model for blind students. During the interview, participants expressed that Markit was learnable, easy to use, and simple to operate. However, some of them also mentioned that they had some difficulty in 3D navigation and face selection. For example, to annotate a continent on a globe model, a maker needs to select all triangular faces, like as you can see from this image. One participant said, the fact that you have all these faces to select just ends up being time-consuming. In the future, we will implement an element detection function. For example, the function will detect the faces of South America by calculating its boundary and combine them into one single item, and a maker just needs to select that specific item. Some prior work already touched this research topic, so we think it will highly improve the user experience of Markit. To further improve the toolkit, we will upgrade the system with new hardware and iterate it in long-term studies. Like iPhone X, more and more smart devices nowadays have a dual-camera optical system, which can provide depth information to accurately track the model. By adding depth information, we may be able to remove tracker and deploy a markerless tracking system. We also plan to iterate the toolkit with blind students, teachers, and makers in long-term studies. In the evaluation study for Talkit, we ask participants to finish tasks as soon as possible. However, faster is not necessarily better. For example, if a blind student is very interested in a model, they may spend more time to explore that model. In the future, we will use other measurements to see what's the potential impacts of these augmented models to blind students. We are also interested in how the teachers design and use augmented models. And we just organized a workshop with them yesterday, so I wasn't here yesterday. And this picture is showing a teachers or visually impaired playing with these models and providing some suggestions for us. We will also iterate the toolkit with broader maker audience. In the future, we will distribute the toolkit in online communities and ask makers to provide feedback to us. In summary, in this talk, I present a low-barrier, computer vision-based toolkit to make 3D printed models talk. From evaluation study, we show that with our toolkit, augmented models are easy to create and easy to use. Thanks.
Yeah. Hi. Hi. I'm Mary from Microsoft. I was wondering if you could comment on the scalability of this approach. So for example, at the beginning you talked about the globe and how the globe is full of textual information, but of course the globe doesn't only label the continents, right? A globe labels information much more densely. It labels all the countries and all the rivers and mountain ranges. And I was wondering why your example globe, for instance, didn't support that level of detail. Is it a limitation of the technique, or would that be possible?
Yeah, good question. So you are asking basically how many information could we contain in this globe model. So in the study, yes, we only contained 5 annotations, but the system obviously can track more, but it also depends on the size of the fingertip, right? And with the size of a globe model, if you contain 10 or 20 annotations on a globe model, it would be very confusing for blind students to explore as well. So one solution we propose, which I also mentioned in the assets paper, is to enable different levels of information. For example, the user could choose to explore the globe model in city level, So when they explore the model with their finger, the system, whenever detects the finger and the globe, will tell which city they are touching. But of course, this will have some accuracy issues. And we talked to teachers of visually impaired yesterday, and they suggest we could also generate models with different sizes and embeds different information in that case. Hope this answers your question.
And I had one other question. It looked in your video. So I understand that, even though they're holding it with all their fingers, the tracker is just working because of whichever finger they have the sticker on is what it pays attention to. But it looked in the video like the person had to make sure, like, to be pointing at something on the opposite side of the model that was facing them so that the camera could see their finger, which seems, I don't know, like trying to imagine it, it seems like that would be uncomfortable. Like I would imagine that more naturally I would be pointing at something near me. So was that confusing to people as a way to select things?
So, for our evaluation study, we recruit the blind adult blind participants who have decent skills to map the model back, right? But for blind children, yes, this could be a problem because they may not necessarily have the skill to map all the shape back to their mindset. So we are deploying the system into wearable nowadays, and we hope we can put wearable cameras or something from their egocentric way to check the model. Yeah.
Thank you.
Thank you.